welcome everybody. It's a great pleasure to welcome you to the second talk of the term, our DSS series, the CCMA Distinguished Speaker Series. I'm Professor Lydia Bouriba, organizer of the series, which was founded in 2015 in honor of Professor Cheng Mei, who is here, second row, for his contributions in fluid mechanics and mechanics, his seminal contributions. So the goal of the DSS series is to provide a vibrant forum for highly distinguished speakers from around the world to come and share basically their frontline research with the CEE community, the MIT community, and the Boston community at large. This series is made possible thanks to the support of the CCMA Fund and the MIT Department of Civil and Environmental Engineering. And I invite you to consult the lectures on the website behind me, dss.mit.edu, where most of them are posted, where you can use them for basically research or teaching or else. So today we're delighted to host Professor Detlef Lohse. Detlef Lohse received his PhD on the theory of turbulence in Marburg, Germany, as a postdoc in Chicago, and later in Marburg and München, I hope I said that right. He worked on single bubble sonoluminescence and then was appointed as chair of physics of fluids at the University of Twente. Professor Lohse is also a member of the Max Planck Society and of the Max Planck Institute of Göttingen and honorary professor of Tsinghua University. Professor Lohse is known for his exceptional contributions in the most diverse fields of fluid mechanics, such as transition between different turbulent regimes in Rayleigh-Bénard convection, Taylor-Couette turbulence, the study of multi-phase turbulent flows, sonoluminescence, inkjet printing, the properties of bubbles and drops down to the microscopic level, and micro and nanofluidics. His research covers both fundamental and applied science and combined experiments, theory, and numerics. Professor Lohse is editor of several journals, including the leading journals in the field, such as the Journal of Fluid Mechanics and the Annual Reviews of Fluid Mechanics. He's a fellow of the American Physical Society of DFD Division of Fluid Dynamics, member of the American National Academy of Engineering, the Dutch Academy of Sciences, the German Academy of Sciences. He also received, in addition to all of this, many other recognitions and prizes, including the APS Fluid Dynamics Prize, the Spinoza Prize, the Simon Steven Meester Prize, the Axov Nobel Science Award, the George K. Batchelor Prize, the Balzan Prize, and this year he received the Max Planck Medal, the highest international award in theoretical physics from the German Physical Society for his research on the physics of bubbles and on turbulence, joining other physicists like Einstein, Bohr, and Schrödinger, who also received that medal, except that his was the first in fluid dynamics. So without further ado, please join me in welcoming Professor Detlef Lohse.
Well, thanks a lot, Lydia, for this kind introduction. It's my great pleasure to be here. I have been here many times, and it's always great to be back, to speak to many colleagues, to get inspired by the nice science going on here. And also, I made it as a great honor to give a talk in this series, and thanks for your support for this. I was also very pleased to see that my friends Stefan Zaleski and Andrea Prosperetti were also speakers in this series, one just 2 weeks ago and one in 2 weeks. So this work is on Maragoni versus Rayleigh, and here you see Mr. Rayleigh and Mr. Maragoni. Mr. Rayleigh, of course, very well known. Mr. Maragoni, less well known. In fact, he was a high school teacher and he also, in Emmanuel Villameux, our joint friend, he stresses this that Maragoni was, well, he is Italian, but he was educated and taught in France. So Emmanuel is stressing this very much. Well, here I will speak on the competition between these two guys. In fact, here's a very famous example for the competition. In fact, it's the tears of wine, which you see here. And well, everybody at MIT knows this, because there have been beautiful work by John Bush and Pekka Hosoi. Well, John is on sabbatical, I understand, and Pekka is doing her duties as department chair, or whatever administrative duties she took, so I don't see her. But I will see her for dinner, I understand. So, and then I will tell her that she missed this introduction here. And so what is the Tears of Wine? Well, you know that. So alcohol is wetting and creeps up this glass, and at some point there's instability developing, and then it's going down. It's creeping up because of the wetting, and it's creeping up of the selective evaporation. So what's happening is that alcohol is evaporating up here. Therefore, the concentration of alcohol locally goes down, surface tension goes up, and further liquid is pulled up. And well, at some point there's this instability. So this is an example of Maragoni pulling it up and Rayleigh, so gravity, pushing it down. Well, this work is in fact developed with collaboration with various colleagues, PhD students and co-workers, and most of the work was done in fact by Yan-Shen Li and by Yaxing Li and by Christian Diddens. And the various colleagues are also involved, including Andrea Prosperetti, who will speak in 2 weeks. Here's the menu. So first I will speak on a jumping drop, and then I will speak on evaporating multi-component droplets in 2 cases. First with weak Maragoni, which leads to segregation of these multi-component droplets, and then with, in fact, a mixture of water and glycerol, which also leads to segregation. Again, Rayleigh and Maragoni in competition. So first, the sudden death of a jumping droplet. This is a paper which came out earlier this year with Yan-Shen Li as lead author. So here you see what we observed. So we have water at the bottom and ethanol at the top. We put in an anise oil droplet. It's sinking as you expect, and then it's jumping. It's jumping at a frequency about 1 jump per minute in this case here. And it's absolutely reproducible. Well, it's sinking, and you would expect that it would find some equilibrium because the density of the anise oil is in between the density of the water and the ethanol. And well, that was the original idea. We wanted to see the behavior of this anise drop in this gradient of density. In fact, there's not only a gradient in density, but also gradient in surface tension. And we wanted to find a stable position to observe the flow around it. And when Yaxing and Shen was waiting for this position to be taken, it would jump up. I'm speaking of this frequency of about 1 jump per minute. I'm not speaking about this wiggling. So this wiggling is this Brun-Veselier oscillation, which in this case, because of the stratified situation, is about 2 hertz. So this is very well understood. I won't speak on this. I speak on this jumping once per minute. And well, here you see the density and the equilibrium. And here you see the jumping. H as function of time. At about a minute it jumps and so on. And this, in fact, goes on for quite a while. So in this case, you have about 30 to 40 jumps. And then it stops from 1 second to the other. In fact, Yan-Shen was coming to complain that this thing doesn't find its equilibrium position, but was always jumping away when he adjusted everything. Then he came to my office, and I had a look. And well, then, in fact, it was here. And I said, what do you want? It's sitting there peacefully. And it turned out to be reproducible. So it jumps about, say, 30, 40 times, and then it just stops. And we call it sudden death of a jumping drop. So what's going on? Here you see more information. We have different sizes of droplets, and it's sinking. And you see that the time between the jumps is getting longer and longer and longer. And in fact, it diverges. This is when it stops. So it's diverging, and then here it goes to infinity, so to say. You see that the driving force for this jumping seems to expire after some time. So what's the difference between a particle and a droplet? So for a particle, you would expect it assumes the equilibrium position, and indeed it does. And well, it goes down exponentially, and this can very well be calculated, and this has been done in this very old paper. But what happens for a droplet? Well, you have Maragoni flow. So there's not only a gradient in density, but there's also a gradient in surface tension. And this oil droplet has higher surface tension at the bottom, where you have water, than at the top, where you have ethanol. And so you have this gradient in surface tension, and this also drives the flow. And this is what, in fact, is the origin of this jumping, as you will see. So here, there's this flow which is driven. And here is the visualization of this flow. So you see Maragoni flow in this direction. And that Maragoni flow is inside, but in particular also outside. And it's like a swimmer. And, well, here it's going down. This is a PIV visualization. And this, watch here, it's getting stronger and stronger and stronger, this Maragoni flow. And then it jumps up and so on. So it's Maragoni drag, which pushes it up, and gravity, which pushes it down because it's slightly heavier than the ethanol at the top. And then it's a swimmer, and well, the swimming community is called a puller. So it's moving like this, and then it's shooting up. Well, here you see the connection between this jumping and this Maragoni flow, Maragoni velocity. So we measure the velocity right here. And here you see this velocity and the velocity of the drop, and there is a clear correlation. So it is really this Maragoni flow which is the origin of the jump. And you will see that this Maragoni flow is growing exponentially. And it is this exponential growth of this Maragoni flow which is the origin of the jump, and I will explain this in more detail in a second. Well, here's the mechanism. It's a swimmer. I mean, it's a typical puller in the swimming community, and it is this Maragoni flow at the side which pushes it up. So two components of the flow. There's a buoyancy jet around this particle that had been calculated in this paper. And there's this Maragoni flow, and they are in competition. What we see here is the stagnant cap. The stagnant cap is thanks to surfactants. So it's, of course, unavoidable. You have lots of stuff floating around in the water, and we always see the stagnant cap here, which is, so to say, an artifact of the surfactants, but well, therefore it stops a little bit earlier. But overall, the mechanism is unchanged. Well, then you get a flow reversal once this Maragoni flow is taking over, and you get this positive feedback. So what's happening is that this Maragoni flow is driven by the surface tension difference between here and here, between here and here. And this surface tension difference is increasing because the Maragoni flow brings down ethanol-rich liquid from the top to here. Therefore, the difference in surface tension between here and here is increasing because all of this ethanol-rich stuff is coming down, which reduces the surface tension here. And as the difference is then getting larger, the Maragoni flow increases, more ethanol is being brought down, and the effect is, so to say, getting stronger and stronger. So it's a linear instability leading to exponential growth. Well, here you see this transition, the buoyant velocity versus the Maragoni velocity. This is the exponential decay of the buoyant velocity, and the competition here. So this is the buoyant velocity, and this is Maragoni. Here they meet, and here Maragoni takes over, and this is when you have the jump. And well, you see both velocities as function of time, and it is really this Maragoni flow which drives it up. This flow reversal triggers the jump, and here you explain now the exponential growth. So this velocity is pulling down the ethanol-rich stuff, and well, in first approximation, you assume that this Maragoni flow is the difference between concentration here and here. When you take the derivative, you get this, and then you Taylor expand, and then you get the second derivative of the concentration, as a prefactor between the derivative of the Marangoni velocity and the Marangoni velocity itself, and this, of course, gives you exponential growth. Remarkable thing is that in this approximation, it is the second derivative which determines whether it jumps or not, and this is, of course, kind of peculiar, and I will revisit it. But the exponential growth is correct. You can see from this plot. So this is a log linear plot of the velocity versus time, and you see here a linear line, so corresponding to this exponential growth, and this is indeed happening around here when the Marangoni flow takes over. So why does it die all of a sudden? Well, it jumps 30, 40 times, but of course it introduces some mixing, more and more mixing, and then at some point the growth would take longer and longer and longer, and well, then at some point, yes, you still have this exponential growth, but then at some point it's not enough to overcome the gravity, and then Marangoni no longer wins, but Rayleigh wins. So delta C, the difference because of the mixing, goes down, therefore Marangoni goes down, and at some point, in fact, it doesn't win anymore. And this is happening with increasing time, which you see here. And so here I put it into pictures. So this was a situation what we had before, that right here Marangoni would take over. But well, then once you have more mixing, then at some point it would take over later. This leads to the increase in the delta T between two jumping events. And well, I mean, at some point, in fact, you're in this situation, and then it falls dead, and then it doesn't jump anymore. So there's no flow reversal, and then, in fact, Rayleigh wins and not Marangoni. Well, this is the first case, the second case, and then it falls dead and no jumping because of this mixing. So you wonder, is this all correct? And a good way to test is to do numerical simulations, and these are brute force numerical simulations with this OMFIP code. This is the object-oriented multiphysics finite element library from Manchester. I will come back to this later. And that is what Christian didn't use. And on the left, you see the concentration, ethanol concentration, and inside and outside. On the right, the velocity. And the thing is sinking down. And you see the flow pattern. And exactly what I told you is happening. No stagnant gap, of course. In the numerics, we don't have surfactants. And fortunately, so the stagnant gap, of course, is something which is there only in the experiment. But otherwise, exactly what you see, and here it's jumping, and this goes on. It's axial symmetric code. Well, this represents the jumps in a very nice way. And we can compare. Here you see the situations of the flow as function of time. So the first jump here and the second jump here. And we see what I told before about this exponential growth. And so this is all holes. And just here, this is just before the jump or during the jump and so on. And we can even compare one-to-one the experimental situation here and the numerical situation. And we see very, very close correspondence, apart from the fact that here you have the stagnant gap because of the surfactants, which you don't have here. But otherwise, it's all the same. So the numerics also gives the opportunity to revisit this strange result, that it is the second derivative of the concentration, which would determine the slope of this exponential growth. Is this really true? So, well, you had seen my question mark here. And we can now measure, in fact, the concentration at A and B as function of time and see whether this is really the case. So we measure the concentration at A and measure the concentration at B in the numerics. And what we see is the following. So here, CA is red, CB is blue. And when you focus on here, you see that CB, in fact, is not changing that much. in fact, it's mainly Ca, and here in the rear during the jump, not much is happening. So you see this again here. Well, we can zoom in into this time here, or zoom in even further. And you see that basically Cb is constant here. And the interesting things are happening at the top. It's a puller, as I said before. It's not a pusher, it's a puller. And when we put this into this calculation here, we can forget about this because Cb, in fact, is constant. I mean, we saw that. So we forget about Cb. Cb is 0. We measure this in the numerics. It's only Ca and the change in Ca. And then what we get is still exponential growth, but it is now the gradient of the concentration and not the second derivative, which is honestly also was more intuitive for me. I was always very surprised that it was the second derivative which was supposed to determine it, but indeed it is not. That was simply from the assumptions that also Cb would change, but we saw in the numerics that it is not. And from the experiment alone, of course, there was no way to find this out. We really needed the numerics to find out what is the determining factor. And it is the gradient and not the second derivative. And with that, we can now explore the phase space. So we take the gradient here in phase space and the size of the droplet, and then we look when the anise oil is jumping and when it isn't. So black means no jump, and red means a jump. And what you see is that strong gradients help to jump, what you would expect. And also large droplets jump. And somewhere in between, there is this line, which we are now exploring, where exactly it is happening. So let me show you two cases. So here, it happens to be that we have a small droplet and a large droplet in the same situation. In fact, it was not a controlled experiment. Somehow, by mistake, a little droplet ended up here. But you see the difference here. The little droplet right here is not jumping, whereas the big one is jumping. And, well, for the same stratification here. So here it's jumping, and, well, this guy is not jumping. What you also see is that these experiments with anise oil are not so well controlled. And the reason is that anise oil we had, for traditional reasons, we had looked quite a lot into ouzo, which is a ternary liquid. Basically, ethanol, water, and anise oil, and that's why we played with this anise oil. But the anise oil, in fact, has some solubility in water and ethanol, and over this 1 hour experiment, it would lose a little bit of mass, about 10%, and that's why, in fact, it's jumping higher and higher and higher, which you saw in this. So you will see, you've seen in my plot, it's jumping higher and higher. This is kind of an artifact, and we then decided to go to a more controlled situation. We went to silicon oil, and we also wanted to make this gradient really extremely well controlled. And well, it's always nice to visit labs. And this morning I was in Lydia's lab, and well, visiting labs always is inspiration. And I had visited quite a few labs from the geophysical people who look into stratified flow. So Bruce Sutherland and Paul Linden and people like that in that community. And they have stratified flow where they have salty water at the bottom and in fact, fresh water at the top, and they really can build a stratified profile in a very nice way with the so-called two-bucket method, which is a beautiful way to do it. And we adopted this to microfluidics, and in this way we could produce a very pure gradient, and then we would take an oil, silicon oil, which has no solubility whatsoever, to really get control experiments and to explore the phase space. And well, we also go to dimensions which are more common in the geophysical community. This is the Sprund-Vicelia frequency. It's basically the gradient of density, in fact, mapped to a frequency. So this is the parameter which characterizes it. And Well, here this is the density matched situation. Well, this is the data, so we take a silicon oil droplet which would settle down there. And then we would do a controlled experiment in this case, and this is what we would get. So here is the inverse Brunt-Vasilia frequency, and here is the radius. Red means no jump, and black means some jump. And you see that basically there are two regimes. So here, the critical radius beyond which you would see a jump goes like 1 over n. And well, here it's steeper, 1 over n squared. And we would like to understand this. So how to understand this scaling behavior. And therefore, Yan Shen dug out this beautiful paper from Young, Goldstein, and Bloch, JFM, 1959, motion of bubbles in a vertical temperature field, temperature gradient, and there the solution is known. It's Stokes flow, it's a creeping solution where you really can calculate everything. So UR and U theta, and what we take as Maragoni flow is the velocity at an angle of 90 degrees. So the velocity right here, that is the strength of the Maragoni flow. So in fact, that paper studied the weird phenomenon that a bubble in a liquid which has a temperature gradient can in fact go down. Normally you would expect, well, all bubbles rise, but once a bubble is small enough, it is this Maragoni flow which drives it down, and they found this and compared it with the theory. And I mean, this paper, by the way, is only 7 pages long. We speak a lot on JFM rapids. 10 pages is enough to convey something and so on. Well, this paper is 7 pages. It provides both the theory and experiment. And it's cited, many, many million times, hundreds or thousands of times, a beautiful paper. And that we used and adopted to our situation. So the Maragoni velocity is shown here, coming from that paper. And we define a Maragoni number with this Maragoni velocity. And what we see is that when we then translate this experimental data into Maragoni, versus the inverse Brunt-Vasilia frequency, we see that this critical curve corresponds simply to a critical Maragoni number. The Maragoni number has to be large enough for this instability to develop, which is very intuitive, right? I mean, like in Rayleigh-Bénard, the gradient must be strong enough, and then you get these convection rolls, and here the Maragoni number, the driving force must be strong enough, and then you get this transition here. You can also make this guy non-dimensionless. You can go to a Wormhousley number. You could also go to a Rayleigh number, and this is ongoing work to also put this in the framework of Maragoni versus Rayleigh and to get this phase diagram. So what we also find is that in fact for a large Brunt-Vasilia frequencies here, there is a different slope, which we also now understand. But I mean, I don't want to go too much into detail. I only restrict myself to this case, and there's simply a critical Maragoni number. And well, what you would expect is much larger than 1, and well, it happens to be 750. You may argue it's large. But well, the onset of Rayleigh-Bénard convection is at 1708, so it's also large. So in this sense, it's still order than 1. I mean, 2 pi to the 4 is also still order of 1, so it happens to be 750. So, well, on the jumping height, so what's the jumping height? And the maximum height. So here, this is the height of the jump, and this is the maximum height. In fact, there's yet another height, and this is the height which we call the top height, when the linear gradient ceases. Well, we looked into how these heights look like, and we find the remarkable result that larger droplets, well, they do jump, but then the height of the jump itself also depends on the droplet. And in fact, those droplets which jump highest are the droplets which are the smallest ones. So here, these are the smallest droplets, and they jump highest. They, in fact, they jump nearly up to the maximum which is possible. It means they jump up to here. If they are even smaller, they don't jump at all. And that we don't understand yet. So that we are still figuring out with these very controlled experiments. Good. So this was the first part, and I will now go to evaporating multi-component droplets. So here we had this multi-components, 3 components, ethanol at the top, water at the bottom, and ethanol and oil in between. But I will now go to 2 other multi-component cases to look into evaporation. And again, Maragoni flow is driving it. And I will first start with binary droplet evaporation. And with the ethanol-water mixture, where also Maragoni flow is driving. Here, ethanol-water are perfectly miscible, as we all know. And we will analyze this experimentally, but also numerically. And I had already mentioned this code, which had been developed by Andrew Hazel and Matthias Heil in Manchester. It's arbitrary Lagrange Euler finite element method. And it's put into this object-oriented library, which I can really highly recommend to you. It's beautifully done. It's easy to use. And well, here you see a case where droplet, in this case, a single component droplet is evaporating, and you see this adoption of the grid. And the code is ideal for that. And you can add many, many things. And this is what Christian did. So here we look into the pure droplet evaporation, vapor concentration. Outside, it's driven by the diffusion equation. So evaporation of a droplet is all controlled by diffusion outside. And, well, of course, we have Navier-Stokes equation. We have the stress boundary condition. And we have kinematic boundary condition here. So it is the gradient of the concentration field which determines the evaporation rate. And, well, we put this together. And we can also put in a second component. In this case, it's water and glycerol. And there you get a solute Maragoni flow. So the reason for this is that the highest evaporation rate is right here. And as you have high evaporation, here you get then a gradient in surface tension. And this drives this Maragoni flow because of the selective evaporation. And once you want to program that, then we, as a further equation, we must put in the water mass fraction or glycerol mass fraction. The material parameters are all known. So surface tension, how it depends on water concentration, density, viscosity, and diffusivity. This is all very well known, and you can put this in from tables. And then really calculate the full thing. And then for the flow, of course, Navier-Stokes equation and mass conservation. And well, one result is shown here. And this is now ethanol water, binary. And in fact, in this case, it's also ternary, but I will stop it when it comes to the ternary part. So here I draw as in color the concentration of ethanol. And what you see here is that at the edge is going down because the evaporation rate is highest. Therefore, water concentration is higher here. And therefore, surface tension is higher here. And therefore, this liquid is pulled down. So it's pulled down here, and you get this flow. And at some point, in this case, because it is ternary, the ethanol concentration is locally so long that you get a nucleation of the third phase for this ternary droplet. I mean, I took this movie because it's nice, and it's a good demonstration of this Maragoni flow. So this Maragoni flow can get so violent that you can even break the axial symmetry. So that code assumed axial symmetry, But when you look in experiments, you see that you get axial symmetry breaking. You get these vortices here. In fact, it's so fast, it's about 1 millimeter per second. It's really very violent flow. So a Marangoni flow, solidal Marangoni flow is a very strong effect. So here the volume is going down with time. And well, we eliminate here. And of course, once the ethanol is evaporated, there's no strong Marangoni effect anymore. And then the flow breaks down. But well, that takes some time. And in the beginning, you have a strong Marangoni flow. And you get all these vortices here. You see here up to here is still vortices, but well, at some point it gets weaker and weaker. It's still evaporating here, but not driven by these very strong concentration gradients anymore. So here you have these vortices, and well, they die out, and then here it's axial symmetric again. And here's the time. So here, this is the time when we look into it during that time. And you see that after 150 seconds, it has died out, which holds both the average velocity and average vorticity. But there's still evaporation ongoing. But the strong driving by Marangoni flow at some point is expired. And then it gets axial symmetric again. So this happens, in fact, even well, this happens when this ethanol is gone, because then you don't have any gradient in surface tension anymore. It's further evaporation, so it's still going down here, but slower. And you may want to expect that there is still thermal Marangoni. Because when water is evaporating, or ethanol is evaporating, it costs a lot of energy, latent heat, and then locally it would cool down, and you have a temperature difference between the edge of the drop and the center of the drop, and you would also get a Marangoni flow, a thermal Marangoni flow. And this clearly is the case, but it's very weak. So whenever there is so little Marangoni flow, it will be the dominant effect. So thermal Marangoni effects are very weak here. Here we compare things. So of course, you could do the numerics also in 3D. And here we have a one-to-one comparison between the numerics of this process and the experiment, and really a one-to-one even quantitatively. So this breaking of the symmetry is also reflected in the numerical simulations. So you want to compare it one-to-one, and red is experiment, and blue is the numerical simulation. And you see a one-to-one correspondence. You may argue, why are the curve on top of each other? Well, it's also a linear instability, so exponential growth here. But when it sets in, depends, of course, on the initial distortion. And the initial distortion in the experiment is higher than in numerics. I mean, in numerics, we have only numerical noise, whereas in experiment, you have also all kind of uncontrolled things. So therefore, because of the initial larger distortion, it's faster in experiment as compared to the numerics. But, well, I mean, it's the same result. Of course, you can plot them on top of each other, and you see that then it is the same. Good. So with this, I come now to binary droplet evaporation and segregation in this binary droplet evaporation. And this came out of a collaboration with Lohse. So Lohse, now bought by Canon, is a company in inkjet printing. And one of the crucial things, of course, the ink. And the ink is multi-component. And when the ink is on paper, you have selective evaporation. But also when the ink is on the nozzle here, you have also selective evaporation. And where you have conflicting requirements. So on paper, you want a fast evaporation of the ink. And on the nozzle, you want slow evaporation of the ink because you want to have controlled conditions. So if the mixture of the ink and one component is evaporating, then the properties of the ink on the nozzle is changing, for example, surface tension, and then you would have to apply a different pulse, in this piezoacoustic inkjet printing, to jet the ink. depending on how long the waiting time was. So you don't want that. So, and then the company, the scientists of the company must somehow look into this, how to handle these conflicting requirements. And one of the test inks, in fact, is Exxon Dial. And that's why we looked into this Exxon Dial water mixture. So the real ink is, of course, top secret. Well, Exxon Dial water, well, this has very similar properties as the real ink. And we looked into that. And we will see that we get a weak soluble Marangoni flow and segregation thanks to that. And the second case is water glycerol mixture, and there we also get segregation, and there the segregation is thanks to gravitational effects. And these are these two papers. But first I come to Exxon Dial water mixture, and here you see confocal microscopic movie. Blue is water, and yellow is Exxon Dial, and we let it evaporate, and what you see is segregation. And that's pretty remarkable because these guys are miscible, water and Exxon Dial, perfectly miscible, but during the evaporation process, they segregate. And you wonder, well, why is this ongoing? Isn't Marangoni flow mixing the stuff sufficiently? But it isn't. So you have selective evaporation. In fact, here water is evaporating, and therefore you get Marangoni flow, higher surface tension thanks to this Exxon Dial. And here you get higher Exxon Dial concentration here. Here you have a higher water concentration, and therefore you get, in fact, Marangoni flow from here to here. And that would drive some convection role, but you now must compare the timescales. This convection role driven by Marangoni flow with this evaporation timescale. And in fact, when this evaporation timescale is shorter than this timescale, then the flow is not strong enough to compensate for this evaporation, and you get segregation. So what's happening is that outside, the Exxon Dial concentration will go up and will shield the water inside. It's trapped. Of course, if you wait for a day, you get diffusion, but the convection by Marangoni flow doesn't sufficiently mix the interior of the droplet, and therefore you get segregation. So insufficient mixing and segregation. So that's the mechanism. You get locally very high concentration of this 1,2 Exxon Dial, and you trap the water inside and protect it from the evaporation. And Exxon Dial has very low volatility, basically zero, and that's trapping the water inside. So here you see the bottom view showing this trapping mechanism. So remember, oil is the yellow stuff, Exxon Dial. So here it's now all trapped. Water is inside but cannot evaporate, and leading to segregation. Very unexpected. Well, we could also do micro PIV here. Well, I will rush through this. I will basically explain that. And well, here's the mechanism. And in fact, in a parallel paper by Howard Stone's group, they also found this. The nice thing is it's the same mechanism, but it's a different liquid and a different method. And well, they appeared around the same time. So Yak Singh was very happy that he was a little bit earlier here. Come on, it's not so important. It only shows that you do work on something important because other people do it too. And then it was also covered in Focus on Fluids. So this article covered both articles, both in PRL and in JFM. So it was somehow, it was so to say in the air. And well, it's not so important who was first. And well, I'll come back to this, by the way. So here I could go now to another case, glycerol-water mixture, binary droplet. And, well, it's a submillimeter droplet. And what we teach our students is if the droplet is submillimeter, so if the bond number is smaller than 1, then gravity shouldn't play any role. This is what we teach in elementary fluid mechanics. You see, gravity wouldn't play a role. And this is the case for water, for droplets with water or with also the mixture or with glycerol. We wouldn't expect this to have any role. It's perfectly spherical cap, and gravity doesn't play a role. Well, that's wrong, as you see here. So it's a sessile droplet of this mixture and a pendant droplet. And you see, when we go slightly above the surface, we see the flow going inwards here, whereas for a pendant droplet, it goes outside. Very different. How can this be? I mean, we just saw bond number is smaller than 1. And well, the reason is that, yes, bond number is smaller than 1. The shape is spherical cap, but because of selective evaporation, you can have accumulation of one liquid, the accumulation of glycerol, and this introduces a density contrast. And that will then drive some convection, some convective flow. So you see here, now we go a little bit higher, and we see these convection rolls developing, and that's in fact driven by differences in density. So here you see this too. And convection rolls, and well, also in the numerical simulation, we see these rolls for sessile droplets. And then we compare with pendant droplets, so this is coming here. Pendant droplets, we also get rolls, but they look very differently. So pendant rolls, it looks this, going out here and going in here, so it's the other way around, both in the experiments here and also in the numerical simulations. So here we compare these two situations. Sessile droplet rolls in this direction, pendant droplets rolls in this direction. Very, very different flow patterns. So clearly gravity must play a role. Also in the numerics, here direct comparison between sessile and pendant. Both convection rolls, but very, very different. Right? I mean, if gravity wouldn't play a role, this would be identical, but it isn't. Major differences. So, well, how come? Well, the reason is that here also sessile versus pendant droplets in the numerical simulation here, very different behavior. But the reason is that the selective evaporation introduces density gradients into the liquid, and those drive a flow. And the number to characterize is Archimedes number or also Grashof number here. So it's a difference in density and then a non-dimensionalized. And well, the Grashof number is nothing else but Rayleigh number divided by Prandtl number. And here you see Mr. Grashof and Lord Rayleigh. Grashof, in fact, did quite a bit. So I think he didn't get enough credit. He was professor in Karlsruhe, and he really had quite some deep insights. So Gareth McKinley, he is always interested in these people. So Grashof would also someone who I think would deserve your attention, and you deserve further research work of you, what he is doing, and also would deserve to have some anecdotes told about it. I don't know any anecdotes on Grashof. I think he did great work, and I think he didn't get enough credit, but he did quite a bit, in fact. So here you see what's the effect of this Grashof number, Archimedes number. This was a case which we had before, sessile versus pendant, very, very different. But once the Archimedes or Grashof number is smaller than 1, then this effect goes away. I mean, then the driving of this difference in density is no longer strong enough. And you see that then, once Archimedes number is small enough, sessile and pendant droplet would just behave the same here. So it's really this Archimedes number, which is the control parameter for this gravitational instability here. And, well, here you see the conclusions. So gravitational effects play a dominant role in this evaporating glycerol water binary droplet. It's gravity-driven effect caused by this density difference, which is a density gradient which develops thanks to the evaporation. And the control parameter is the Archimedes number. So here you see those two cases here. And well, here Yaxing, in fact, was less happy. So we, because there was parallel paper, so this was received 5th of September 2018, and then we had it back from the referees, and during that period, this paper appeared. And in fact, they were earlier, about half a year earlier. They basically found the same. Again, different liquids, also a very different method to measure it, where they didn't supply numerics, but well, basically they found the same. So again, it was in the air. When this, I mean, now I repeated to Yaxing, it's not important who is first. And this time it was very helpful for him. It simply shows it's relevant, and it's a very relevant question. So the more general conclusion is that it is both Marangoni flow and gravitational convection, which can be relevant. And there's not only the Marangoni number, but also the Rayleigh number, or Grashof number, Grashof-Rayleigh divided by Prandtl. And that made us look into this in a more general sense. So we looked into the phase space, Rayleigh versus Marangoni, and looked at the quasi-static case. So I showed you many movies as function of time, but now I show you a movie in phase space. So this is where you are in phase space. So in this case, in fact, the Rayleigh number is 10 to the 4, and Marangoni number is in fact 1. And this is the flow pattern there. It's quasi-static, which is appropriate because this evaporating process is all very, very slow. And so the flow, in fact, is always in its quasi-static situation. So this is how the flow looks like. So in fact, here Rayleigh wins. And now you have both Rayleigh rolls and Marangoni rolls in this. Now, in fact, Marangoni wins and Rayleigh loses, totally dominated by Marangoni flow. Now we go to pendant droplets, which you can think of a negative Rayleigh number. And here, in fact, Marangoni wins. And here, again, competition, Rayleigh versus Marangoni. Both roles exist. And here now Rayleigh wins. And no Marangoni flow. And, well, now we go back. So it is the flow pattern can, in fact, is determined by both Marangoni and Rayleigh. So they're really in competition. And depending on where you are, you get one or the other pattern. And up to now, people had focused either on this or only on this axis. But you see it's somehow richer. You can have one or the other case. I mean, the nicest case, of course, when you have both roles. I mean, Marangoni flow and Rayleigh flow at the same time. And, well, let me end with this slide to thank my co-workers, in particular Christian Diddens for all the numerics, and Yan-Shen Li for the jumping droplet, and Yaxing Li for the evaporation droplets. And I can assure you that they are no twins. One is postdoc and one is PhD student, but they are both great. And while I take questions, I show this favorite movie here. That you can enjoy the complicated flow structure for this movie and Mr. Rayleigh and Mr. Marangoni being in competition. And during that, I will take questions. Gareth wants to contribute an anecdote on Grashof.
No, I know nothing about Grashof yet. Yeah. No, I wanted to ask in the first part, the separation between the dependence on the second derivative and the first derivative of concentration. One of them ends up with a very explicit dependence on the radius, and the other one doesn't. So you have two criteria. One is dependent on R and one is not. Did you investigate that?
So well, we investigate this. Indeed, it is the linear dependence, which is the correct one. Where is the calculation? So it is this, and so what we now find is that it is really this criterion which sets the onset. I mean, later, I mean, this is only for weak gradients. For stronger gradients, things become more complicated. But for weak gradients, it is really consistent with this picture here.
Yeah, but your experiments show, you mentioned that you're still investigating this dependence on radius, because you do see a transition. So,
yes, yeah.
So that's a difference between a weak gradient and a strong gradient.
Yes, exactly, yeah. And with the other one, I mean, this is developing. I mean, we have some more results, but my academic teacher, Todd Dupont, always said I like fresh salad, but I don't like fresh results. So this had to settle still a little bit, but it looks like there are these two regimes. So.
It looks very interesting.
You also know Todd, so you can see Todd telling this. Yeah.
And then a very short question on the second part. What sets the critical Marangoni number for the onset of the symmetry breaking or the axis? You show that you see...
That's a very good question.
Yeah.
So that I'm sure would come out from a linear stability analysis of the flow. So what we are now doing is that we look into the axial symmetric flow and do a linear stability analysis of this numerically and see when the eigenvalues are getting positive and see what the driving is strong enough. But that's major work. And in fact, this is a colleague of mine in Shanghai is doing that. Who is expert for this kind of spectral analysis of flow. But I would be extremely optimistic that this would come out. I don't know at what Marangoni number, but I hope indeed that it is this critical Marangoni number which we see that we also see in the experiments. So when this would occur.
Thank you.
Perhaps the PhD students or master students at MIT could do it as a homework, but it's major work, right? I mean, what you have to do a spectral thing. Basically, you have to do what Orszag did for Poisson flow, where he got this 5,700 in Reynolds number with the spectral methods. It's a numerical stability analysis, and you have to do this for this geometry. And we can't give this as homework problems in Twente, but perhaps at MIT, I think the students should do this. So yeah, it's a good exercise. Yeah.
It's a very great talk. So I just curious for the water and the glassware mixture job, because the water and glassware has very different viscosity. I just wondering, like, would the viscosity matters in the evaporate of the flow during the process?
Well, I mean, the viscosity would also then be inhomogeneous, just like the density is getting inhomogeneous, and you would also get inhomogeneous viscosity during this evaporation process. So in this sense, the Rayleigh number which you ascribe to it, it's also somehow, would locally differ, just as it introduces differences in density and also introduces differences in viscosity. But what drives the flow is, of course, the differences in density.
Okay.
And the differences in viscosity would stabilize this.
Okay, thanks.
Other questions?
This part use a droplet that is partially miscible to the other two fluids. Right. And in the final numerical simulation, the late experiment it changed to silicon R. So, and we noticed that in the first experiment, there are also concentration of ethanol in the droplet. So I just wonder whether this partial miscibility may change the scaling of everything.
That's a very good question. So what we did originally are these experiments here, and what you see is that remarkably the jump gets higher and higher and higher. Yeah. Right. And the reason seems to be that you have a certain loss. In fact, you have solubility of this anise oil in the surrounding, in this ethanol water mixture. But on the other hand, you also have ethanol water going in there. And well, that messes things up and makes them less controllable. And that's why in the well-controlled experiments, we go to silicon oil, which has zero solubility or close to zero solubility, both in ethanol and in water. And then we get a more controlled situation. And well, all these jump heights, which I showed you later, well, they are not changing in time. I mean, here, the changing in time is thanks to the solubility.
What is the solubility inside this droplet? Can it induce additional internal subflux and then change the scaling of?
Yeah, well, this is very slow. A very weak effect. I mean, I don't think that this would change the scaling, but it changes a little bit the height and screws things up a little bit. But I mean, the mechanism wouldn't be changed. I mean, solubility is not that high there. When you see it takes an hour, and then in an hour it in fact loses about 10% of mass.
It's actually a very tiny question. It's just in the selective evaporation. I was wondering, do you have an idea of the size, like what selects the size of the rolls? Like when we look at the periphery of the droplets, you start with a lot of the recirculation cells of one liquid. Do you have an idea how it's selected?
Well, I mean, you saw the movie here, this final movie. You mean this length scale here? What sets this?
Yeah.
I mean, it's this complicated balance between these two effects. So on the one hand, driven by density differences, and the other hand, driven by Maragoni flow. And what it exactly sets? Well, I mean, I think you calculate the strengths, and either one or the other wins. I mean, you see, I mean, it can be any, depending on where you are in parameter space. It can have any widths. I mean, the extreme cases being pure Maragoni or pure Rayleigh, and then it takes over. But I mean, what we can't do is that you say, okay, you are here in parameter space, calculate the exact thickness of this flow. I mean, that we can't do. I mean, I don't think it's possible. I mean, you simply have to solve it numerically, and this is what you get. Yeah.
A little bit related to 2 questions ago, when the drop is not miscible in the surrounding fluid, in the jumping drop case, does it still die? Because the explanation for the dying in the miscible case was that there's local mixing. Does the jumping stop after a while in the case of silicone oil in the ethanol?
It's still mixing. Yeah, I mean, it's mixing it doesn't dissolve, but it's still, by going up and down, it mixes the gradient, the external gradient. It will still die.
Okay.
So you have still water at the bottom and ethanol at the top, but well, I mean, it really will mix, and then it's still going. Probably we didn't look into the long-term behavior there, but well, I mean, it dies. I mean, when exactly it dies, I mean, that's also. It's very difficult to measure, and well, it depends on the size, and we haven't looked into this systematically. But it's not only the mixing because of the solubility, but it's also of the mixing because of the movement. I mean, you stir, so to say, and in this sense, it will still die. Presumably, it will live a little bit longer than in the other case, but how long, we didn't look into this.
Okay, that makes sense. Thank you.
Yeah, I may miss that. What's the speed of that vertical jump? the scale of the speed?
Well, I mean, let's look into it. So you see that here it jumps by a few millimeter in very short time. So a few millimeter in fact, less than a second. I mean, I can't give you a more precise number. We can resolve this, but then you need high-speed cameras. We didn't do this yet. But it's, I mean, as compared to this thinking here, it's extremely fast. We can look into the Maragoni flow here. We have this values here where I show this curve. I mean, here you can see the numbers from here. So it's, well, I mean, here it diverges, but this is 0.1 millimeter per second. So this is, I mean, it's relatively fast.
Okay, yeah. Another question. So basically, currently, it's like a kind of infinite domain, right? The droplet is like unbounded domain moves.
Well, I mean, at some point it's bounded because you have only a finite region where you have this gradient. I mean, at some point there's no gradient anymore, and then there is no driving force, and then of course it comes to a still set. This is what we called a ceiling here. I mean, here we have these plots where we, I mean, it can of course only jump in this region here. It can't jump beyond the ceiling, and then
I mean sideways, then in horizontal direction is basically unbounded. I'm just wondering if you put like side restriction, like if you put a droplet into a very thin column. Like,
well, I mean, then you have, of course, some damping effects because it's from the sidewall, and the overall flow development will be hindered, and then, well, at some point you make it so thin that you will partly screw up the effect or hinder it, but we didn't look into this. So right now we have relatively large containers to avoid the edge effects. I mean, it's complicated enough, and we are glad that we don't have edge effects, and we don't want to bring them in.
Yeah, I understand. Yeah. Just because like, the block ratio, if it's finite, it can. I'm just guessing it may be able to like stop.
This is from the side, and well, here this is from the top. I mean, this is unavoidable, obviously, right? And well, from the side we didn't look into this. So our cells are large enough that we think that the edge effects are small.
Okay, thanks.